Let's have a look now at the idea of spans. What do we mean by a span? Again, the idea of a span is related to that of linear combinations. In fact, the two come together in the definition. Okay, so if I pick a set of vectors, any set of vectors doesn't have to be a subspace, just any set. In fact, it could be a finite set. In fact, it could be just a set consisting of a single vector. Just pick a bunch of vectors in a vector space V. Then the set of all possible linear combinations of the vector in this small set is called the span of the set, and is denoted by span S. Okay, not a very imaginative notation, is it? So what we do in order to consider the span of a set of vectors is we start from a set, and then we say, all right, what are all the possible linear combinations that I can get from it? So in particular, if I start from a finite set v1, v2 up to vn, so I take a small finite set of vectors, then its span is going to be given by the set of all possible linear combinations for all possible scalars that I can pick between negative infinity and infinity. Okay, so this is what is going to make up my span. Okay, and so it's just a larger set. It's something where we start from the building blocks, these vectors in the finite set, and then we're starting from there. We're going to build any possible linear combination. Now remember, linear combinations are one of the key concepts here. It's the one that is equivalent to the closure axioms, therefore is the one that defines subspaces. In fact, what we're going to see very soon is that the ideas of spans and subspaces are really two sides of the same coin. It turns out, in fact, that spans and subspaces are really the same thing. In what sense? In the following sense. The span of any set of vectors is always a subspace of V. Okay? And the reason for that is that the closure axioms both hold because we include all linear combinations, right? So remember, so basically I'm using the linear combination axiom. Because I'm including all linear combinations, well, that means that if I start from any vectors in my set, in the original set, and I consider any linear combination, I'm still in there. And so in fact that's what's happening with this span. Not only that, but this is one little thing that you may want to check, and this may be a difficult line for you to parse, but linear combinations of linear combinations are also themselves linear combinations. Okay, so if I start from two linear combinations of vectors in my set and I combine them into linear combinations, what I come up with is just a linear combination of the originals. It's just a matter of rearranging it. You may want to double check it also to make sure you understand what this sentence is actually saying. Okay, but basically, the closure axioms have to hold. There is nothing that can go wrong with that if we're looking at the span. So every span is always a subspace. On the other hand, the opposite is also true, and even more easily. Any subspace is always the span of a set of vectors. Which set of vectors? All of the vectors. Okay. A subspace is closed under linear combinations, right? So what I can do is I can think of it as the span of all its vectors. Again, think of all its vectors, think of all the linear combinations of all these vectors. Well, we're not going anywhere else, are we? Because the subspace is closed under linear combinations. And therefore, subspaces and spans are actually the same thing. And what we're going to be doing in the next few classes is we're going to see how this relationship allows us to develop a few more concepts related to vector spaces and subspaces, and allows us to get a whole bunch of other pieces of information about these objects.